Okay, so welcome to the first in-person lecture of Calc 2 Math 140 Spring 22. And so what I want to do today is just use the time to go over and review material from Calc 1. So we've already had a lot of reviews already. The more reviews we have, the better. We can use this as a springboard to talk about the need for theory. You are taking this from a math class perspective. We prove things. You are not going to be responsible for proofs on the exam, but you should at least know why something is true. And the reason for this is you have less of a chance of misusing something if you know where it came from. So you don't have to be able to reproduce everything, but it's good to know why these things are true. And that will often help you in terms of solving problems. So today, we'll do some differentiation problems. I'll talk about the need for theory and its applications of the theory as time permits. Just some classroom policy. So the policy is if someone's cell phone goes off in class, everybody gets a quiz the next class. So if you're the phone that goes off, everybody will know. My cell phone is 617-835-3982. If mine goes off, I have to bring a donuts, munchkins, whatever. Are we allowed to have food in class right now or no? No, okay. So you will then get a quiz in the bank. So in previous years, I've always done it that if someone's phone goes off, either have a quiz for everybody or you have to bring breakfast for everybody. Since we can't eat in class, I will do instead, if my phone goes off, and by all means have one of your friends try to call me if you want, then you would get a quiz in the bank. If you speak up in class, you can grab a piece of candy on the way out, or you can even grab it now. You can take a piece of candy before class begins as a advance, and then you're just on the hook for speaking up at least once in class. I really want to get you in the habit of speaking up. A lot of the questions are straightforward. The reason is later in life, they won't be. And I want you to be in a point where you will be noticed later in life. There are so many smart people out there in the world. You want to make sure that they know that you have the ability as well. Are there any specific topics from Calc 1 that people want to review? If not, I'm going to start off with a monster derivative. Okay, and so again, the whole point of this is to show how cool I could be if I wanted to. Your saving grace is whatever I give you, I have to grade. So that will limit my cruelty a little bit because I didn't have to grade it, oh my God, how many times? So let me give you the following function. Let's say f of x is 3x squared x plus 1 e to the 2x to the 4th plus cosine of sine of cosine of x cubed. 1, 2, 3. Right? If anybody is excited about taking the derivative of this, you need seriously. Right? This should not excite you. Yes, I can do this. This is the 21st century. If you really wanted to take the derivative of this, you would plug this into something like Wolfram Alpha or Mathematica. And if you just plug it into something like Mathematica, let me shift what I'm sharing. If I shift to it's just something I was doing for the school early today. Okay. So let's find for derivative. Is this large enough that people can see? So I would remove it just a little bit. I can say, okay, so it would be 3x squared. Of the sine of x cubed. What's nice is you can see the parentheses are in different colors. As I hit things, they highlight where it's going to. And I do comma x. And so D stands for derivative. And what do you think the comma x stands for at the end? The derivative with respect to x. This is a very respectful class. With respect to x. X is the variable in play. Later today, I will be teaching multivariable calculus. The only real difference there is we now could have 2 or 3 variables that would differentiate. And so I could have a function of x and y, and I might say, what's the derivative with respect to x, keeping y constant? And so I hit Shift Enter to compile, and there's the answer. So again, in the 21st century, this is how you would find a derivative for something like this. So Why are we still having you learn how to do things the long way? It's nice not to have to resort to the computer every single time. It's also nice to have some intuition of what the answers are like. It's nice to be able to follow some of the proofs and arguments in other sources. Okay. So let's take something like this. So the way you handle this is you always hack away. So I have a nasty expression like this. I have a bunch of rules of differentiation. Have I given you the baby guidelines as to how to do mathematics with a newborn baby? So the first time I taught differential equations at Williams, my daughter was born early in the semester. And when you have a newborn baby, babies cry a lot. Why does the baby cry? Any thoughts? It needs something. Thank you for not saying, you kicked it. Yes, good. Baby needs something. What does the baby need? What could it be? Food. What else? Change. Sleep. Attention. Burping. There's lots of things, right? And so when you are a young parent and the baby is crying, what do? You try everything. Right? It's like Zootopia, try everything. Is it this? Is it this? Is it this? Is it this? And eventually you hope one of the things works. After a while, you start to realize, wait a minute, that's the I'm hungry cry. Wait a minute, that's the I want to be held cry. And then you know what to just go to. If you don't know what to do, just try everything. And eventually you realize which is the one that works. When I defended my PhD thesis, there were two non-mathematicians in the audience, my wife and one of the deans, because I did a lot of stuff for social life for graduate students. And afterwards, my wife said, that's your I nervous voices, right? That's the voice you used when you asked me out the first time. I haven't heard that voice in years. You eventually start to recognize. So we have a lot of different rules of derivatives we could use. We have the sum rule, the product rule, the quotient rule, the difference rule, the constant rule, the multiple rule, the power rule, the chain rule. And you always want to ask, which is the first rule that comes into play? So when you look at this messy thing, which rule do you think comes into play first? The sum rule. So sum rule first. So sum rule first. We can write f of x as a of x plus b of x. So f prime of x is a prime of x plus b prime of x. So now we've reduced the problem to two smaller problems. And this is the general goal. We always want to take something complicated and keep reducing it to something easier, easier, easier. Eventually you get to the point where you have to do something. Right now we're just setting things up. Okay, we have A and B, we have to find A prime and B prime and then put them together. Which would you rather do first, A or B? A. Is that just because it's listed alphabetically first? We've got A first. Does A look a little bit easier or harder than B? If you're comfortable with the chain rule, B is actually not that bad. If you're comfortable with the chain rule, you're not comfortable with the chain rule, B is pain. A is unfortunately not quite something we're used to. So A of x, boy, somebody was mean, is 3x squared, x plus 1 times e to the 2x to the 4th. What rule would you love to have used for? So what rule you? You'd love to use the product. Why can't you use the product rule? So one thing is we didn't learn the product rule with three functions. Well, one possibility is derive the product rule with three functions as an aside, and now you just have that in your arsenal in the future. Or we know how to do the product of two functions. What could we do? Absolutely. Which two do you want to combine? Okay, so we could combine these two, and let's call this C of x times D of x. Why didn't I do B of x times C of x? We already have a B, so I can't use the letter B. So I've got C of x is 3x squared x plus 1. D of x is e to the 2x to the 4th. C prime of x if you remember the product rule, I can just write it a little bit quickly. I'm going to just do that as 3x squared prime times x plus 1 plus 3x squared times x plus 1 prime. Right? Derivative of the first times the second plus the second times the derivative of the first. What's the derivative of 3x squared? 6x. So we have success, we got 6x times x plus 1. And then we have plus 3x squared times the derivative of x plus 1, which is just 1. So if you wanted to simplify, it would be 6x squared plus 3x squared is 9x squared plus 6x if you wanted to simplify. Okay. How would we take the derivative of d of x? The 2x to the 4th. What? Yes. And so what is the rule you're using? Anybody remember the name? Chain rule. So I can write d of x as e of f of x. So e of input is the exponential of input. F of x is 2x to the 4th. And now we see e of f of x is going to be e to the 2x to the 4th. E prime of x is just e to the x. F prime of x is 8x cubed. But we need e prime of f of x, which is e to the 4x squared. And now d prime of x by the chain rule is e prime at f of x times f prime of x. The f prime of x is the most forgotten part. And so that would just be e to the 4x squared. E to the 4x squared times 8x cubed. And so putting all of that together, that would give us the derivative of the first part. So any questions on how we calculate this derivative? It's not pleasant, but if you just keep breaking it into smaller and smaller pieces, it's not so bad. Now, yes. Coefficient in front of the, oh wait, I shouldn't have called this D because we've already used the letter D. Oh, no, that's fine. Sorry. This is okay, what was your question? In front of the E? Okay, so are you talking about little e of big E? Okay, we have little e to the 2x to the 4th, right? And we want to take its derivative. So this is going to be the chain. And so we're writing this as basically the composition of functions e of f of x. And so if f of x is 2x to the 4th, my rule is e of input is e to the input. So what would e squared be? It would just be e squared. E to the 5th, e to the 5th, e to the smiley face, e to the smiley face. So if I now plug in not x, but f of x, I'll get e to the 2x to the 4th, which is my function. What is the derivative of just the function little e to the x? The derivative of the exponential function is the exponential function. Yes? Oh, at the very bottom. Oh, at the very bottom. Oh, I'm sorry. Yes. I flipped the order of the two. Yes. Is that what the question was? Okay. So over here, I flipped the order of those two. So this should be 2x to the 4th. Okay, so my rule is exponential of input. And if my input is 2x to the 4th, I get back my original function. Now, what's the derivative of the function little e to the x? It's just little e to the x. But where do I evaluate it? The chain rule says D prime is E prime at f of x times f prime. So I have to remember that I'm evaluating the derivative at f of x. And so I have my function big E. Its derivative is itself because it's the exponential function. And then I have this extra f prime that I have to put in. So there is one thing I wanted to just mention over here. We had a of x was 3x squared x plus 1 e to the 2x to the 4th. And we wanted to use the product of what we couldn't because it's a product of three functions. Is anybody familiar with New England transcendentalist writers? This is a liberal arts college, so this is a fair game question. Okay, who do you know? Excellent. Thoreau is actually my favorite. And when I was a postdoc at Brown, there was a rich donor who loved Thoreau and donated a lot of Thoreau material to the Brown Library, including his Harvard math book. And so they reached out to the math professor. Sure, I'm happy to take a look at them. I actually saw Thoreau's math books. So I believe Thoreau is the patron saint of mathematics. He has phenomenal advice that we should all take to heart. So what's Thoreau's most famous work? You have a 50-50 chance. Walden. The other possible one is, oh, you've got so much extra credit today for knowing things. So Walden and civil disobedience. So what is the big piece of advice from Walden? His advice to people. Two words. It's actually the same word twice. Simplify, simplify. So if you spent a year living on Walden Pond, trying to get away from everything and just simplify his life. Now, of course, you could simplify to simplify, but I think the extra simplify really drives home the point. So before you do anything in mathematics, you know you've made it when your name becomes a verb. You Thoreau the expression. You try to simplify. Could you take this function that's the product of three functions, and is there a nice way to write it as a product of two functions? You've got three functions right now. Could you somehow rewrite it as a product of two functions?
It'd be like,
yeah. And so if we do it like this, we get rid of one entire product rule. So simplify. So eliminates a product rule. It is not wrong to do it as a triple product, but you can make your life easier if you first notice, hey, wait a minute, if I just take a moment and simplify. So it is very easy to mislead. It takes a while to learn how to do algebra properly. So I'm going to see if I can stop the screen share and get this to work for a second. So I love Rubiks Cubes. It takes me about an hour to teach someone how to do a 2x2 Rubiks Cube. So, oh good, so you can see over here. So this is a standard 3x3 Rubiks Cube. Okay, I'm not that good. It takes me about 1 to 2 minutes to solve something like this. The world record is on the order of like 5 seconds. It's absolutely amazing. Right, how many sides does this have? 6. How many pieces on each side? 9. Here is a Rubik's Cube. How many sides does this have? 6. And on the top, the yellow, 9 pieces. 9 pieces. But when I start looking at the sides, how many pieces do you see on the sides? Yeah. Looks very different, right? If you try to turn the red side, it doesn't quite turn. Which cube do you think is harder to solve? They're the same. Why? Right, so if you hold this at a 60-degree angle, all of a sudden, this becomes one of the sides. And it is almost the same. It's actually slightly harder than this. And the reason is this one doesn't have any pictures on the centers. So if the centers are rotated, you can't tell when you solve it. Whereas for this one, there's a little bit of an issue with the centers, but it's essentially the same kind of cube. If you imagine this having pictures on it, it would be the same. I always like to bring these to emphasize the importance of looking at things the right way. If you look at things the right way, you can make your life tremendously easier. So much of math is finding a way through the algebra. And this is also one of the reasons you take a class like this. When you start to get very long expressions, can you somehow look at them and get a sense of what's going on? Order of magnitude, can you tell me what's happening? It is too easy to just have tremendously long involved calculations and have no real idea what you're talking about. I just read a wonderful book talking about how to put mathematics into numbers that we can understand. And occasionally in my life, I've seen something like this. How many people have taken the physics class and know a little bit about radiation? So if I gave you some numerical values of radiation, would that mean anything to you? What do you need me to do for it to be meaningful? I'm sorry? Okay, but if I do the wave, would that mean anything to you? If I give you a number, how do you get some sense as to what that number means? So you can describe the effects of the human body, give some kind of interaction you might understand it, or relate it to something that you understand. So how many people have had x-rays of their teeth? Okay, what does the doctor do? And if they don't do this, I'm going to have to talk to you after class. When they take your x-rays, they what? Yeah, they put a thick blanket of lead. Why? To protect you. Like, we didn't know this at first, but x-rays going through your body is not so good. Do you think that's enough protection? Yeah. They make sure they protect you. So I was reading this book and I was trying to describe how energetic the radiation was, and it said, imagine a lead shield stretching from the sun to Pluto. This would go through them. But okay, I now have some understanding. I know the normal X-rays we're exposed to, a little shield about this thickness is enough to stop it. This would go through something from here to Pluto. Okay, got it. But so you always want to try to put numbers in context. So when you're trying to explain something, how likely is this? I was talking with some people about how dangerous COVID is. And when you look at young kids, more kids were dying from drowning in certain age brackets, young age brackets, than COVID. And so something like that helps you make a more informed assessment of risk. You always want to put numbers in context. You always want to try to simplify things and see if there's a better way to do it. So there was nothing wrong with doing it as a triple product. But if we take a moment of time and think about what's going on, we can actually make our lives a lot easier. So the next part I want to do was the second part, was the b of x. So we have b of x was cosine of sine of cosine of x cubed. 1, 2, 3. And then the chain rule is if we have g equals u of v of x, let's see, actually this should be g of x. G of x is u, I'll do w of x. Then g prime of x is u prime at w of x times w prime of x. The w prime is the most forgotten piece. People always forget the w prime. And the reason is if I give you x to the n, what's the derivative of x to the n? N times x to the n minus 1 times the derivative of x. What's the derivative of x? It's just 1. And so what I like about the iPad is it's easier for me to switch colors. And so because it's 1, we don't write it. But when you think about the standard power rule, the 1 is there. When we're doing the chain rule, we have to remember the w prime at the end. So I could go through this very, very slowly, or what I can just do is I'm going to just try to do a little quickly. So b of x prime is going to be cosine prime at sine of cosine of x cubed times sine of cosine of x cubed prime. So I'm just doing the chain rule rather than just writing out here's my first function, here's my second function, I have enough confidence in myself that I can just write it as derivative of the first, evaluated the second, times the derivative of the second. And it makes sense when you're doing the chain rule that it's u prime at w of x. It can't be u prime of x because initially I had u at w of x. So if I'm evaluating u at w of x, I should be evaluating u prime at w of x. So that's the second most common mistake, is people evaluate u prime at x, not w of x. All right, what's the derivative of cosine? Negative sine. And so the really bad mnemonic I have is you have to remember there is a minus sign, and the minus sign is minus sine. So the derivative of cosine is minus sine, the derivative of sine is cosine. To see this, if you go back to the unit circle, at some point here, this is the point cosine theta, sine theta. As you start at 0 and you move up, cosine starts at its largest value, and then cosine gets smaller. Well, if cosine is getting smaller, what must be true about its derivative? It's getting smaller. The derivative has to be what? Negative. So you're getting small, the derivative is negative. Okay, that's why it's minus sine. Whereas sine starts off at 0 and is getting larger. So the derivative of sine has to be increasing. And since cosine is positive in the first quadrant and sine is positive in the first quadrant, the derivative of cosine has to be minus sine. The derivative of sine has to be cosine. All right, so I know it's going to be minus sine of cosine of x cubed. Now I have to take the derivative of sine of cosine of x cubed. What rule do I use? Chain rule. And so of means chain rule. So whenever you hear of, you should be thinking chain rule. So it's going to be sine prime at cosine of x cubed times cosine of x cubed prime. Okay, so it's negative sine of cosine of x cubed. Again, I will make all these slides available. 1, 2, 3. And the derivative of sine is cosine of x cubed. What's the derivative of cosine of x cubed? It's going to be cosine prime, and then the derivative at x cubed, then the derivative of x cubed. Can I just go straight to the answer at this point? Okay. So then it's just going to be derivative of cosine is minus sine of x cubed times 3x squared. And that would be this case. Essentially, any derivative problem I give you is going to be along these lines. I can't give you something you can't do. There is no excuse for getting a derivative wrong. There is every excuse for getting an integral, for being unable to do an integral. Most integrals cannot be done in closed form. And most of the time when you teach calculus too, they don't tell you this. They make you feel like you've learned all these techniques for integrals. So hopefully you've seen a little bit of integrals or antiderivatives at the end of your Calc 1 class. It's going the opposite direction. So derivative, I give you a function, what function is the derivative of this? Antiderivative goes, what function is the derivative? There is plenty of functions I can write down where we just have no expression, no closed form expression what the antiderivative is. So you are not expected to be able to find every antiderivative, but you're absolutely expected to never write down a wrong antiderivative. So if you think something is the antiderivative, what can you do? Check it, right? Check it. So it's okay if you don't know how to find it, but if you have an answer, you can always check and see, does this, when I take the derivative of this, do I get back what I studied? I suggest checking it on a separate piece of paper so you're not looking at things. It's very easy to be guided by what's on the paper. All right, any questions on this differentiation so far? So these are all the different rules. What I want to do is I want to talk a little bit about where these rules for derivatives come from. How many of you are thinking of being a pure mathematician for the rest of your life? Okay, so I was expecting this, it's just me, that's fine. How many people think you're being some type of scientist? What if I threw in economics and psychology? Okay. Not quite willing to, I'm not going to get there with this being recorded. Okay. So if you're doing science or related fields, you're going to be gathering data, you're going to be conjecturing, you're going to be trying to come up with, here's my hypothesis. We can do that with mathematics. A lot of mathematics is presented almost from the Moses school of mathematics. And Moses comes down from Mount Sinai with the rules of derivatives or whatever. And these are divinely inspired, and this is how it is. Let's try to see if we could derive what the rules should be. So let's take the product rule. Is there anybody in class, let's say A of X is F of X times G of X, who would like to have supreme power over the universe? Anybody? You look willing? All right, so you now have supreme power over the universe. You're going to create the universe. You're going to do a much better job than what we have now. No fully better. So what would you say the derivative of a product should be? If you were going to make the universe, how would you make it? So we have the derivative of a sum is the sum of the derivatives. What would you choose for the derivative of a product? The derivative of a product is the, what do you think would be a nice rule to remember? Here, it's not.
Are you looking for the actual?
No, I'm not looking for the actual. I'm saying you get to redo things. How would you make the product rule if you could redo things? So you would make the derivative of a product the sum of the functions? You can do that. You've got supreme power. I think you want to put derivatives in it somewhere. So what would you have as the derivative? Oh, we got an excellent. We got one from Zoomland. Excellent. Multiply, then differentiate. So why don't we have the derivative of a product is the product of the derivatives? Wouldn't that be a much nicer rule? Life would be so much easier. What would you have the quotient rule be? Derivative of quotient is the quotient of the derivatives, right? It's not that way. Now, we hopefully all remember the product rule, especially since we just used it a few moments ago. Let's try to experimentally derive the product. So what I need is I need three functions. I need a function f of x, I need a function g of x, and I need a function a of x, which is f of x, g of x, where I know all three. So can somebody give me a function where I know its derivative? A nice, simple function. X squared, what else? X cubed. So more generally, I could take something of the form x to the n. I could just do x squared, but I can do more this way. And the more things I can do, the more evidence I'll gain. Which I take for g of x. Another simple function. Sorry? I could do x plus 2, but that's going to now give me a sum. So I could make it a little bit easier and just do x. Well, instead of just doing x to the first power, what else could I do? I could do x to the second power or third power. So I could just do x to the m over here. And n and m give me two free parameters. So rather than doing just the special case 2 and 3, what you could do, let's try to do a whole slew of things as well. It's not terrible to do x plus 2 because we know the derivative of x plus 2. But this gives us a nice large swath of things to try. So what would f of x times g of x be? That'd be x to the n plus m. Well, we know f prime of x is n x to the n minus 1. We know g prime of x is m x to the m minus 1. And we know a prime of x is n plus m x to the n plus m minus 1. And so it seems to reason a prime of x maybe is a function of f of x, g of x, f prime of x, g prime of x. You know, a is made up of f times g, so maybe the derivative of a should be made up of the functions and their derivatives. And so is there any way to combine f, g, f prime, and g prime to get a prime of x? Well, we see a prime of x has x to the n plus m minus 1. How can I get a term x to the n plus m minus 1? Any thoughts as to which ones I can combine? Sure. So I'm trying to get a prime of x. I believe a prime should be a function of f, g, f prime, and g prime. I know a prime of x is n plus m times x to the n plus m minus 1. So the key thing is it has n plus m minus 1 powers of x. Looking at f, f prime, g, and g prime, is there any way to combine that stuff so that when the dust settles, I have a term that has x raised to the n plus m minus 1? So if you look at f of x, that's an x to the n. I want to get x to the n plus m minus 1. So how many more powers of x do I need? I need m minus 1 more powers. Who could give me m minus 1 more powers? G prime. So I could look at f prime of x times g of x. That will give me, I'm sorry, I'm doing it the other way here. I could look at f of x times g prime of x. Or if I looked at g of x, that's x to the m, how many powers do I need for that? I want to get to the n plus m minus 1. I've already got m. I need another n minus 1. Who can give me n minus 1 powers? F prime. And we would just write this as f prime of x, g of x, plus f of x, g prime of x. This is a better way to write it. You start off with the first function, its derivative, and you always do the order f, g, of g. And it turns out this does equal a prime of x. This is evidence. It's not a proof, but it's evidence. If you want for a more interesting example, you could do f of x is cosine x, g of x is sine of x, and then a of x is cosine x, sine of x, which is the sine of 2x over 2, if you remember your trig identities. So you could actually use that, and if you remember your trig identities, I'll make this extra credit. You can use this and show that this is even more support for the product rule. It doesn't prove that the product rule is the case, but it provides you more support and more confidence that it's right. Any questions about this? So this is experimental science. Is we take some simple cases, we explore them and see what we can get from it. The proof is by doing nothing. So mathematicians are lazy. There are two ways to do nothing. How can you do nothing to an expression? Multiply by 1, excellent. Or add 0. And one of my professors at Yale remarked, actually, the log of 1 is 0. So there's really only one thing you can do. There's one nothing like sine. Okay, let's do nothing. Let's let a of x be f of x, g of x. Then a prime of x is the limit as h goes to 0 of a of x plus h minus a of x over h. That's the limit as h goes to 0 of f of x plus h, g of x plus h, minus f of x, g of x over h. Okay. Does anything look strange here? Yeah, there's a really large gap between the two terms that I'm subtracting. And it's because I want to add something in place. And I want to add something that's going to have no change. I've got to add 0. Well, I want to somehow, from my intuition from the last page, I expect it to be f prime of x, g of x. What's f prime? F prime is f of x plus h minus f of x over h. I've got an f of x plus h over here. Let me subtract off f of x. Well, since it's being multiplied by g of x plus h, I'll subtract off f of x, g of x plus h. And then I have to add that back in, f of x, g of x plus h. And so I've just done nothing. And now if we look at the next line, this is the limit as h goes to 0. I'll have f of x plus h minus f of x over h times g of x plus h plus f of x, g of x plus h minus g of x over h. And now I'm going to be a little bit cavalier. The limit of a sum is the sum of the limits. The limit of a product is the product of the limits. You know, these are all the case if everything is fine. So as h goes to 0, what does g of x plus h go to as h goes to 0? Just goes to g of x. What does f of x go to as h goes to 0? So as h goes to 0, what does f of x go to? F of x, there's no change. No matter what value of h you give me, I'm just going to be f of x. What does g of x plus h minus g of x over h, what does that go to? Not 0. We have 0 over 0. Think back to the definition, g of x plus h minus g of x over h. What's that the definition? That's the definition of the derivative of g. The definition of the derivative, g of x plus h minus g of x over h. It's the infinitesimal change in the function divided by the infinitesimal time that elapsed. So this is the average speed from x to x plus h. And as h gets smaller and smaller and smaller, the average speed is going to converge to the instantaneous speed. So this is just the definition of the derivative. So this is just g prime of x. This is why we started, what is a prime of x? A prime of x is the limit as h goes to 0 of a of x plus h minus a of x over h. Now we're just using the definition of the derivative with the function g. And now the last one, we have f of x plus h minus f of x over h. What does this go to? It just goes to f prime of x. And there's the product. So this is called the QED symbol. It means done. Quo demonstratum, that which was to be shown, we finished the proof. So this is how you would prove the product rule. We go back to the definition of the derivative, and then think back to the Rubiks cubes. We have to do some algebra. As we try to do things in such a way that we can see where we want to go to. The hard part of this was subtracting and adding f of x, g of x plus h. This is like drawing the auxiliary lines in geometry. Yes.
So we like explain why you
Yeah, so in fact, that's what I was supposed to do. So perfectly timed. So this is like the auxiliary lines in geometry. Is if you draw the right auxiliary line, then everything is golden. But how do you know what line to draw? Well, the reason I know what line to draw is one, the method of divine inspiration. I know what to do. But two, if I go back a page, we actually did some experimental mathematics. And we looked at some functions where we knew the derivative, and we knew the derivative of the product, and that made us conjecture that the product rule was f prime g plus fg prime. So we know that we want to try to find a way of writing this as f prime times g plus f times g prime. And so when you look at this, I've got an f of x plus h over h. I've got other crap as well. I've got this g of x plus h term, but it's starting to look a lot like an f prime. I've got an f of x plus h over h. And so if I subtract off f of x, g of x plus h, then notice the first part is going to look a lot like f prime of x, g of x. And in fact, it will converge to that as h goes to 0. Yes. I'm factoring out the g of x plus h from the first two terms. And for the second two terms, I'm factoring out the f of x. And I know to do all of this because I have some inkling as to what the answer should be. So now, let's do three functions. So let's say we have f g prime, f prime g plus fg prime. Is everybody okay with me just not writing the at x, just to save a little bit of time? So now let's do fgh prime. Well, I can write this as fg times h prime, and it's now going to be two functions. So that's going to be fg prime times h plus fg times h prime. So that's going to be f prime g plus fg prime times h plus fg h prime is f prime g h plus fg prime h plus fg h prime. Oh. So if I have a product of three functions, it's f prime gh plus fg prime h plus fgh prime. So if I give you fghi prime, anybody want to guess? Yeah. Yes. And so it's actually not that bad to extend the product rule to finitely many products. And so we could have actually just used this immediately. One of the whole points in life is mathematicians are lazy. We like to isolate results so that we don't have to go back to the beginning every single time. We don't like to go back to the definition of the derivative. So we like to extract rules so that whenever we see a product, we can just use the product form. It's worth extracting the triple product so that if we ever have a triple product, we can just quickly quote this and not go through all of that pain as before. Eventually, the formulas become so bad, it's better just not to memorize them and just use them as needed. But the more things you know, the more chance you have of being able to look at something and see relationships. So, this is a quick review of Calc 1. For tomorrow's lecture, we're going to do the fundamental theorem of calculus. And so if I give you some curve from A to B, and here's y equals f of x. So let's let integral from A to B of f of x dx is area under y equals f of x from x equals a to x equals b. The fundamental theorem of calculus says if f is nice, it is big F prime of B minus big F prime of A. And then mathematicians can take turns trying to impress themselves with what is the weakest class of nice functions where this is true. And so if the function is continuous, so it has no jumps, and it's bound, and its derivative exists, then it's continuous, and its derivative is bounded. So what does it mean to be bounded? It means the sum number may be 1,000, such that it's always between negative 1,000 and 1,000. Most nice functions will satisfy these problems. These are not big asks. And so as long as your function is nice, the area under the curve can be found by doing these antiderivatives. So I'm going to have you watch the lecture on the fundamental theorem of calculus at home. How many of you have seen a proof of the fundamental theorem of calculus? How many of you have seen the fundamental theorem of calculus in one of your classes? Okay, so a lot of you have just said you've seen the fundamental theorem of calculus, but your teachers did not prove it. They basically did the Moses, here it is. Okay. Fortunately, the math covers my expression. Yes. Oh, yes, thank you. I forgot to say. And big F prime equals little f. Yes, that's, without putting that in, that's very bad. It's the antiderivative. Now, the antiderivative is not unique. It's unique up to a constant. How many people have taken a physics class? So in physics, you sometimes talk about changes in potential energy. If you start over here and the object falls, the potential energy is converted to kinetic energy. Well, I only care about the change in potential. Where is zero potential energy? Is it at the ceiling? Is it at the floor? Is it at the desk? Is it at my hand where it lands? Is it where I stop? It doesn't matter where you choose your zero potential energy to be. We don't care about the value of your potential energy. We care only about the change in potential energy, the potential energy that's now becoming kinetic energy. That's the whole point of the plus C in the finite derivatives. All right, so this is a good place to stop.